Good morning, good evening, wherever you are, and welcome to this ESIG webinar. I'm Julia Matevosyan, Chief Engineer of Energy Systems Integration Group, or ESIG. I would like to welcome you to this monthly webinar series and give you a little bit of background on ESIG. For those of you who is new to ESIG, we're a membership-based nonprofit organization providing our members with objective information, resources, networking opportunities in support of energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resource materials. If you are new to ESIG and you like what you hear, I strongly encourage you to follow up with us, and I think you will be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all of our working groups and task forces. You can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. ESIG also serves in a leadership role in a Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze rapid clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of 5 pillars of GPST, which deals with research agenda of the system operators. More information on GPST can be found at www.globalpst.org. Okay, so a few logistics before we get started. The phones will be muted for the duration of the webinar to avoid any unnecessary distraction. For the Q&A, we are using Slido platform. So to ask your question, please go to slido.com and enter code ESIG30 as an event code. The instruction, you can also see them currently on the screen and will be reposted in the chat. You can use thumbs up button next to the questions to allow us to prioritize the question. You can cast your vote for the question that you are interested in. We plan to have about 10 to 15 minutes Q&A at the end of this session and wrap up at the top of the hour. An email with the link will be provided once the video has been posted, and we also plan to provide short responses to all unanswered questions after the webinar. So please don't be afraid to ask your questions through Slido and also prioritize the questions with thumbs up. All right, so to introduce today's topic, as you probably all know, renewable generation is dominating the interconnection queues, and legacy synchronous generation are scheduled to be decommissioned in the coming years. These are exciting trends, but also introduces new challenges to maintain grid stability and enable additional new renewable generation to come online. Grid-forming battery energy storage systems has become a well-recognized contributor towards grid stability, and several system operators have announced plans to implement grid-forming requirements in recent months. In this webinar, two subject matter experts from SMA will share recent market news pertaining to grid-forming battery energy storage adoption and functional test requirements. So with that, I would like to welcome our today's presenters, Frank Berring and Lucas Meubrink. Frank Berring is the Director of Business Development, Large Scale at SMA America, a leading global provider for energy transition markets, specializing in power conversion solutions. He has 30 years of experience across technical industries. Frank received his Bachelor of Science in Mechanical Engineering from University of Wisconsin. Currently, he is focused on market shaping and articulating the untapped value of inverter-based resources. His goal is to facilitate the next phase of the bulk power energy transition by highlighting the benefits of potential of advanced inverter-based resources, thereby driving innovation and progress with the industry. Lucas is a senior application engineer. He holds diploma engineer degree in electrical engineering from Technical University in Dresden, Germany. His expertise lies in power systems and energy transition. Lucas' experience spans from technical sales support for both new and second life energy storage products to the design and sizing of grid-scale supercapacitor-based energy storage solutions. For the past 5 years, Lucas has been contributing to SMA as a senior application engineer, where he focuses on energy storage and inverters and grid forming projects. Just a short reminder, once again, to use Slido at slido.com with event code ESIG30 to ask your questions. And without any further ado, let's go ahead and get started. Frank, I'll turn it over to you.
Thank you very much, Julia. Good afternoon or morning to everyone. Thank you for giving us an hour out of your day here to talk about the topics Julia just mentioned. And thank you not only to you, Julia, but to all the ESIG for having us. We really appreciate the opportunity. So with no further ado, this is what we're going to cover today. I will talk about some fundamentals that might be just a refresher for many of you on the line. Maybe it's new to some. We'll talk about what are the fundamentals of grid forming inverters and stability services. We'll talk a little bit about the emerging market requirements. These are not per se requirements yet, but they are announced adoption intentions from a couple of the ISOs. And then my colleague Lucas will take us forward and do a little deeper discussion on the control modes within the SMA inverter and walk us through an example of what could be a future market mechanism in the US. It's not part of the announced plans, but he'll talk about a plant design for a targeted amount of short circuit current. So first, a couple of words about SMA. If you are not familiar with our company, we are a German-based energy transition company that's been around for a little over 40 years now. As of 2023, we were right around $2 billion in revenue for the year. And we operate in 5 different sectors of the energy market and in 3 different segments, as you see on the bottom left there. So Lucas and I are representing the large scale segment, where we operate in PV, in storage, market integration, and power to gas. Not in e-mobility, but our other 2 business units do. And as Julia mentioned, when we talk about grid forming converters here at SMA, we're specifically talking about battery energy storage systems. Not because it's the only place you can technically deploy grid forming, but it is where the technology is, say, the most mature, and it's the application where the DC source lends itself to grid forming applications, I'll say best, because that the predictability of the power and energy in the battery, you always know what's behind the inverter. So in that context, we'll be talking about grid forming today. A little bit of history here for you that I'm sure everyone's aware of, but just to talk you through maybe the last 15 years of deploying inverters here in the US and globally. When we first started doing large scale projects, inverters were pretty simple in the expected behavior. You were operating as a current source and putting active and reactive power into the grid, really to the maximum that the DC source would allow you. And then over time, we the inverter started getting called on to do more, to still as a current source, but to prioritize Q over P in some instances, to curtail, just to do more and to interact with the grid in more ways. And as we see inverter penetration increasing even further up into this 70 to 100% range, and hopefully we'll get to 100% together one day. But we see the need that in order to maintain stability on the grid, that the control mode of the inverter needs to change from being a current source behavior to being a voltage source behavior. And that's what we'll talk about in the next couple of slides. So here I'm going to call attention to fundamentally what is the difference between a grid following inverter and a grid forming inverter. A grid following inverter is what we've been deploying up until recently for grid-connected projects. Grid forming has been around for some time, I think around 20 years for SMA, but it's always been in islanded grid applications. Whereas now we're talking about grid forming in synchronous with the grid, synchronous grid forming. So in a grid following inverter application, the inverter is using its phase lock loop to detect and synchronize to the existing grid's voltage and frequency. And then we control the current from the inverter. Whereas in a grid forming inverter deployment, we are only using the phase lock loop when we first wake up the inverter to detect the targeted voltage and frequency of the grid it's connecting to. But then we never use it again to measure that voltage and that frequency. And instead, we are outputting from the inverter a voltage in synchronous to the grid voltage at a frequency synchronous to what we just measured. And then we can control the voltage magnitude and the phase angle and frequency to manipulate the current output from the inverter. So it's a voltage phaser application. And I will leave it to my good friend Lucas to cover that in more detail in later slides. So in summary, when we talk about synchronous grid forming, we're talking about inverters operating in that voltage source mode in synchronism with a larger connected network. As such, it's able to stabilize weaker regions of the grid and maybe even broader areas of the grid. And it's compatible with the existing generation resources on the grid. And we see this as the manner in which you can replace the stability characteristics of synchronous generators as those types of generating assets get retired and more renewables that are inverter-based resources get connected to the grid. So what stability services does that deployment unlock for us? This slide represents in red the stability services that are only possible with a grid forming converter, whereas those applications in blue that are pretty common can be done with grid following inverters. So starting from 12 o'clock here, one of these new stability services unlocked by grid forming is the ability to provide inertia to the system. Secondly, system strength, operating in an islanded condition seamlessly, and system restoration or black start. Now I will talk a little bit about what we see first globally. Over the last few years, we've seen grid forming requirements coming from different system operators around the world. Probably the most notable being AMO. Australia has been doing grid forming for quite some time. Certainly in Germany, there are some requirements as well. And you've probably heard a lot about National Grid ESO and the projects in the UK, which are, their rules are pretty reflective of this kind of designing to a system strength target that Lucas will cover later in their slides. And then in the United States, just recently in the past, say, year, there have been some proposed adoption coming from a couple of ISOs here in the US that are summarized on my next slide. Started in 2023, I believe in September, with the NERC white paper. And what you see in the table here are basically tests that were recommended. It started with the NERC recommendations for these first tests of how to demonstrate that a converter was in fact grid forming. So trying to put behavioral requirements against this term grid forming. And NERC published a white paper in September of 2023 that outlined these test procedures. And more recently, our friends over at MISO have issued a white paper that I believe is just out for stakeholder feedback that reflects their intentions of how to adopt grid forming capabilities within their jurisdiction. And then even more recently, ERCOT has done the same. And on the rightmost column here, you'll see a comparison against the requirements in Australia, AMO. So there's very much so some similarities across these different entities in what they're requiring to be capable of to be considered a grid forming inverter. But there are some differences, say within each test of how to test it. So the specifics of each individual test protocol. But it's pretty exciting to see this come to fruition. I've personally been involved here at SMA in talking about this for almost 2 years now, and to see some manifestation of grid forming requirements for battery energy storage is quite exciting for me personally. So from here, I'll turn it over to my good friend Lucas, and Lucas will talk to us about the specifics of the control modes in the inverter, and looking forward to the plant design topic that we'll wrap up with. Lucas?
Hello, can you hear me?
Yes, sir.
Okay, next slide. Yes, so I will talking about our control modes and how do we implement these modes best while in the early stage of a project, and how to let's say use it best for sizing purposes as well. Because as we know, many projects in the early phases, and Frank talked about this, it requires a lot of power system studies and different types of modeling exercises to be done, to be performed, to be locally applicable to each project. And for that reason, we will have a kind of a practical session today on how we deal with these kind of projects requests we get, because as Frank said, also it's speeding up, right? We see this industry is changing, and it's I think the speed of change is a lot more than it used to be. So we are very happy to see that, and we have, as you see here on the screen, the different control modes available in our standard software. We're not talking about the commercial process here, but technically, of course, what is available is grid following always, and this is still the majority of projects we are doing. So we have we can give if we are looking at the blue fields here, we can give the inverter obviously a P and a reactive power a Q command. We can also do inverter level P of F and Q of U or Q of V. U is the German way of saying voltage, but that's something we have at the inverter level. So even a function of pushing active power into the grid depending on the frequency, as well as reactive power depending on the voltage, is at the inverter terminals available. And then of course the fourth thing here on the middle, the blue fast dynamic reactive current, that is part of our forthright through capabilities. So we are injecting reactive current based on fault conditions, and by that means we are operating in a very grid supportive manner. And this is also very fast, as I said. But in order to be as fast as rotating machines are, and we need that for higher penetration of renewables, obviously, there's no way around grid forming, right? And we talked about this, and with grid forming, our approach here is we have, and this is in red visible, only available with Sunny Central Storage. So this is our AC coupled inverter for battery storage systems. We have droop, we have a droop mode and inertia mode. What I want to highlight here is that industry-wide, the name for inertia mode is called VSM mode, and there's in the literature there's lots of things to read about this. We don't call it like this. We sometimes give it a kind of the explanation in brackets that it's similar to VSM, but this inertia mode is really an SMA developed mode, which is unique in our firmware, right? So based on these two modes, droop-based is basically for microgrid. So we have droops we can implement, we can set during modeling phase, and we can set these droops, of course, during the commissioning of the inverter for microgrid applications mostly. And for the inertia mode, this is definitely something more to be looked into in detail. What I mean by that is that there are lots of more parameters in the software to be tuned in order to make it work for each project in the right manner, in the right way. So inertia definitely is something which many of you heard about, of course, but it's basically an inherent response to frequency and voltage deviations, and the inverter automatically injects and absorbs active and reactive power and acts super fast according to a traditional rotating machine, especially based on the active power, meaning the inertia. We have an advantage compared to traditional rotating machines because we have the battery, which can produce a lot of active current, which we can use for the inertia. So it's a very tunable device in itself, the inverter, with lots of parameters, right, compared to a traditional rotating machine. And we have a huge active power source behind our inverter, so it's even higher in value when you compare these two technologies. Next slide, Frank. Yeah, so of course, SMA's offering is, when we look at the left side, it's our scope is the medium voltage power station. It's an inverter behind a transformer and including a switchgear. This is the dark gray box in the middle. It's a voltage behind an impedance behavior similar to a synchronous generator. We talked about this. And when we look at these components we have, the same, many of the hardware components are basically the majority is the same for PV and battery applications, regardless of its grid following or grid forming, right? And now comes our enhanced grid forming controls on top of that, which is then acting as a voltage source with true voltage control and instantaneous response. This is what we see here on the right-hand side, right? We have harmonic voltage waveform control. We can operate synchronous with adjustable response. We have overload protection control and many other things, which we also lead together for each project with a team of experts, right? So that's also very important to say here, that we see the need for guided projects in that, right? So we are willing to put in the time and the effort to support each project with very dedicated people to understand the application, to give modeling, and even in some cases also do the actual power system study and support the project from beginning to end, because it's very important for these at least in the early stage, in the beginning, these grid forming projects. When we're looking into 10 years from now, things will be different, but now it's very important to look at the details together and to support each project with the right people and to make it a success. Next slide, Frank. Yes, so when we are looking at the fundamental control capabilities to compare our droop and inertia, we call it droop and inertia, as we have discussed, control modes, and look at the big picture here. What is seen on the left-hand side? We see in green the box. That's something which is always present for each plant. We have a plant controller, which has basically advanced capabilities. You can do overlaid V and F control. You have load adjustments. You can implement the battery management limitations, of course, or you have the BMS directly integrated into the inverter. That's also possible. You do any sorts of grid services by using an external plant controller, right? Energy shifting or fast frequency control. Because we can, looking into the future of this presentation, we can overlay and have multi-use cases for battery storage, right? And that's always also important to mention that traditional applications will not kind of be eliminated by grid forming. You can do many things in parallel, right? And that's the beauty of a battery inverter. So when we look into the yellow box, which is then to the right of the green box, that's our AC voltage vector synchronization. We have these two modes available, or even four, because it's divided into active and reactive power, or Q and P. And this is fully configurable, and you can set the droops and you can tune the inertia as per your need, right? If we look then to the middle of that diagram, it's said AC voltage controller. So that's our software, software current limitation, which then goes into the PWM generation, and the inverter has an additional hardware short circuit current protection, right? And then after that, you have the instantaneous current flow, so the waveform is created. What we have with our V6 bridge, very traditional two-level V6 bridge design, we have a very robust inverter. We have one DC bus and one AC bus. We don't have there's no possibility without topology that there are circulating currents on the DC side or AC side, which leads to a very robust design and a very sophisticated behavior in case of faults, meaning we can ride through any sort of fault you can imagine, and we are successful and we are not tripping. This is based on our robust design. And also what we see, especially for grid forming, and this is what we see in the middle bottom here, robust ride-through plus optional current boost. What we see for grid forming projects more and more coming up as a requirement is a short period of time to have an overcurrent available at the POI. And this capability we can use in an early stage for the project for sizing. So we need to define the quantity in order to meet the exact overcurrent requirements you might see. For instance, there are requirements in the UK we have seen where for hundreds of milliseconds there's a peak needed for the short circuit in that location. We are seeing other things like in Hawaii, where there's an overcurrent requirement on the POI as well. And I think based on the experience the market in general gains over the years, the adaptation of having at least the boost capability more and more in these project requirements will be established more and more, I believe. So we are already having that in our design. considerations. We're giving support not only by sizing, but also by our modeling teams. If we look now into to the right-hand side of this slide, it's explained a little bit with some equations what P and Q droop, as well as the P and the Q inertia means. As many of you know, but the droop is traditionally proportional to the delta of frequency, and the inertia is proportional to the Rokov, the rate of change of frequency. And we have the blue and the red, the K factor, and then the H, so the inertia constant. We have constancy in these equations, which we can use to tune the behavior of that inertial response or of that droop response. We look at to these graphs, we see the grid frequency here kind of collapsing down and then ramping up again to nominal. And then also we have a grid angle, a jump in the graph, and the response we see for these two different control modes. In blue, it's a response from the P droop mode, and in red, it's the response of the P inertia mode. So the main fundamental difference, of course, that the droop response is proportional to the delta of frequency. So it's always present when the delta frequency is present. And even if the delta frequency does not change anymore, but there's still a delta to nominal, we are still pushing power into the grid, right? Until the frequency goes back to normal, then the frequency, then the power also goes back to zero. Whereas for the inertia mode, we are only pushing or we are absorbing when, depending on the rate of change of frequency, and if it's positive or negative, right? If it's going down or going up. And the main difference here is really that the blue curve is really needed for off-grid, microgrid applications, and the red one is needed for on-grid applications. And that's the fundamental difference. We can even think of overlaying these two control modes on plant level. So that's a more sophisticated applications, but still available. Here, these graphs are really, I mean, it's a simple graph, but just to show you how these modes are operating. But we are also working on many other special applications where we are using inertia to make it a pure I application more so, not on the individual inverter level, but that's a very advanced application here. So next slide, please. Yes. So in under any circumstance when running in grid forming, what happens if there's a fault, right? If you have a voltage source and you have a fault and the voltage collapse, you have to provide short circuit current, and how to manage that, right? The inverter should not trip, but it should provide the needed amount of short circuit current into the fault for tripping any protection devices. And also the inverter should not be damaged by that, right? So our approach, and this is not something new, we are using this, we call it virtual impedance mode. We are using this for a long time, also in our smaller inverter classes. But this is something we have developed, and as I said, we call it virtual impedance mode. What does it mean? So once there is a short circuit current, and we see that a short circuit event, voltage is collapsing, some kind of fault. We see this in the first graph. The inverter is inherently pushing some current into that fault, and the inverter is having his hardware protection phase. That's the very initial phase you can see in the second diagram below. That's the current. So the first one is the voltage, and the second is the current. And the very initial phase, there is not a clear sine wave. because the inverters is entering into this hardware protection phase where the voltage waveform is not clear. Once we pass that 1 or 2 cycles, the inverter is by means of that event, it's starting to calculate a virtual impedance value, which is tuned to match 1 per unit of current over the time. And this is exactly what we see. So after the hardware protection phase, so this is the initial peak there, the inverter runs smoothly and entering into a 1 per unit current, because the inverter is basically providing a virtual impedance on its output to control the current, right? So that's what is being done here for, let's say, for the microgrid in group control mode. We're using that for 10 years already. For inertia mode and overcurrent scenarios, it's very similar because we are also having different overcurrent profiles for short circuit purposes, which we also then, it's a more complicated, complex implementation, but in essence, it's very similar. So next slide, Frank. Yes, so let's now look into the more basic versus the more advanced grid forming designs. So it's a closer look at stability services. When we have the generator behavior benefits of grid forming APRs, that's the blue section on top here, we have those main 4 benefits: the instantaneous response to grid events, as we discussed. We have the adjustable power response. The text is a little bit correct here, but we're adapting to changing market conditions. So that's always something we can, along the way, tune parameters to meet new application requirements, right? Or whatever it is, if you multi-stack applications, you have to have some adjustable settings in your plant to react on new requirements. Then, of course, the write-through of extreme events. That's always a strength from SMA to have a very robust design, and we are able to write through all these extreme events, and reduced risk for asynchronous stripping with advanced synchronization controls. So that's also something we are working on, and we have shown in modeling reports that we are very well positioned for that. If we look at the lower section of that slide here, you see basically 2 columns. The first one is the left one, it's basic plant design without headroom. And then on the right-hand side, we see the advanced plant design for stability services. What both have in common is that we have the improved system strength by feature, right? By our fundamental phasor control methodology, right? So that's something which is always present for grid forming, synchronous grid forming, we call it. So there's always for both plant designs applicable. When we now look at the Rockoff inertia or the short circuit current, we can have the first one kind of limited at the basic plant design, or if we look at the advanced plant design, we have tunable inertia for higher than 1 per unit available at all times, and we have a current boost for firm response higher than 1 per unit. 1 per unit here is by means of the POI power. So for example, a 100 megawatt plant would be considered 100 megawatt 0.95, so the equivalent MVA rating would be considered 1 per unit here. And that is something we look at when it comes to advanced plant design. So let's look a little bit more deeper into that. Frank, next slide. Yes, so I talked about the multi-use of battery energy storage solutions already. But when it comes to this advanced control mode or advanced sizing, we really want to need, okay, what are the applications? And a very basic fundamental principle of inertia is that you have to have it always present, because it does not bring any benefit if you're not able to provide the inertial response when exactly in that moment the fault happens. So for that purpose, and stacking of applications makes sense for your business case, then you have to have a kind of a firm power reserve for the guaranteed inertia power. And this is what you see here on this red, on these red boxes for positive and for negative active power. In the middle of that, this is your rated power for arbitrage or for frequency control. So you're operating in that window of available power, but you always have this headroom in the positive as well as in the negative direction to guarantee the inertial response always, right, under any circumstance. So that's the sizing aspect of it. So by that we could do yeah, okay, next slide. So let's look into some examples here. Let's explain the colors and the boxes. So right, so the dashed line in these boxes here is the rated power. The rated power of the plant, as I said, for example, 100 megawatt, 0.95 power factor. This would be the dashed line. And then we have our base case power. No, sorry. The base case power is 100 megawatt. The rated power is the inverter capability overall, right? So the base case power is 100 megawatt. The rated power, the dashed line, is the inverter capability. And the inertia power is the blue line, and the short circuit level is the red line. If you look at plant A, inertia ready, conventional, right? We have the dashed line, that's the inverter capability. So we lower the base case. The base case is, for example, 100 megawatt, and the inverters are designed for 150 megawatt, right? So we use 100 megawatt for the base case power, and we use 50 megawatt for inertia on top of that. And the short circuit current is also 150 MVA, so that's the same. So that's our conventional design, but that's not very best optimized, because if we are looking at optimization for by means of very short duration of, because right, inertia is not needed for hours, short circuit current is not needed for hours, not even minutes. So when we look at plant B, it's inertia and short circuit current. We have the rated base power. This is the dashed line. We have our base case equivalent to site-specific conditions, and then we add our overcurrent boost profile. One portion of that can be used for inertia, so that's why the blue box goes beyond the dashed line, and that's making use of overcurrent for the inertia purposes. And then even for short circuit current, we are even higher. We are using our boost, so it gives you higher availability, higher performance, higher revenue, and it gives you benefits for that purpose. If we look at plant C, that is inertia and short circuit current with SMA boost oversized. So this is really then the methodology for sizing plants for up to 2 per unit or more short circuit current on the POI based on the base case power, right? And if we're looking at the rated power dash line box here, we do oversize the inverters a little bit, but the short circuit current which we can achieve in terms of per unit is much higher than compared to what we have added. So the percentage gain of short circuit current in per unit or in percentage is much higher than we add inverters in terms of quantity. And that's the main message here. So we maximize the revenue and the system stability by doing that. And it's also economically a good option. because we do not oversize by 2 to achieve a 2 per unit short circuit current injection on the PUI. So when we're looking at minimum set of design relevant parameters, this is what you see here on the left-hand side. This is really what we need to look at is continuous power, inertia, short circuit level, and reactive power, and with or without black start. So last slide. So the last slide shows you exactly in practice how we do these things. It's an example plant design exercise, which in essence, to sum it up here again, because of time reasons, we have 12.5% more PCS, more inverters to achieve larger than 2 per unit overcurrent on POI. Right, the process is we are using our sizing tool for that, which we share under A for customers. And by that, we are, for example, doing a sizing for 100 megawatt 0.95 power factor at 40 C. And there's a result of quantity of inverters, 32 inverters, right? That's the base case. And if we're looking at the lower section of that slide, we have inverter level current boost profiles available. We can select. We have different profiles available. And by selecting only 4 PCS on top of these 32, we lower the the base current per each inverter because we are adding some inverters. The total, the one unit needs to provide less current in total to achieve the base case, 100 megawatt, right? But by achieving that, simply lowering a little bit allows us to have headroom in our power stacks to enable our current boost and to provide that 2.3 in that example case here, 2.13 per unit overcurrent on the POI. So this is a practical example of how we do sizing exercises and tailorize these settings according to each project requirement. So there are differences, of course, but that is some major advantage we see for these projects by only adding 12.5%. You have over 2 per unit overcurrent on the PI. So that's all from my side.
Thank you very much, Lucas. I'd just like to add one comment, and that is what Lucas has just shared with you, this approach of oversizing the hardware modestly to achieve an amplified result is not reflected in the emerging requirements from MISO and ERCOT. So they've chosen not to adopt that kind of approach today in their grid forming requirements, but we think it's an important topic and could be very interesting in the future. So I think at this point we can take a few minutes for questions.
Yes. Just first of all, Frank, Lucas, do you have a hard stop at top of the hour? Or can we go a few minutes over just to make sure?
Yeah.
I should probably stop at the hour.
Okay, let's do that. All right, we'll try to hit as many as we can. The first question, most popular one, demonstrating grid forming products is needed and determining its size requires running EMT simulations. Do you provide EMT models at the study stage?
Yeah, the question was, do we? Yes, absolutely.
Next one, on slide 10, how do synchronous grid forming enhance the system strengths of the grid? Are you measuring that using short circuit level only or some other behavior as well? It's a good one.
Typically, yeah, we've had that discussion before, haven't we? Typically, the short circuit level is considered the proxy to system strength, but at the same time, that very quick propping up of voltage does contribute to system strength. So I think the proxy of short circuit current is the most common reflection of system strength and in discussion in the industry today, though.
I'll still put it in a plug that there is a need for a better metric, as you know, inverter-based resources are not best suited for this older metric that comes from synchronous generators. So if someone has an idea, come to us. We'll have another webinar on that. All right, next question. Can older grid following or grid supporting inverter-based resources be upgraded to grid forming with only firmware upgrade? If not, can simple hardware augmentation help here?
Yeah, that's a little bit of a loaded question, and it will vary by OEM. For SMA, the existing generation, and I believe the last generation of battery storage inverters are upgradable. So you can enable grid forming control mode through a software update. You'd have to reparameterize the plant, and you should only do that through a proper EMT study, of course. But it is possible. Older inverters than that, though, like if we go back to SMA's CP series, those are not retrofittable.
So next question is exactly the same, so I'll pass this one. Next one is related. What is the cost difference between grid forming versus grid following inverter? And don't say it depends.
Question. Oh, I failed to mention on the previous question that whether or not hardware changes are necessary will depend on the use case. So generally, it's not required that you have any sort of a hardware upgrade as well. But if you're going to use that asset for black start, then there are some hardware changes that need to be implemented.
So basically,
and coming back to I'm not avoiding the cost question. I'll say that there is a cost associated with it. I'd say at the plant level, it's pretty trivial. At the inverter level, it's a modest increase. There is, of course, amortized engineering and software. When you buy a grid forming inverter from SMA, at least, I can only speak to ourselves here, but what you're effectively buying is a free use license of that software. And there is a price associated with this. But again, it's pretty modest at the inverter level, or at the PCS level. And certainly at the project level, I would even say trivial, but it's not completely free.
Good. Next question from Cameron Cruz from KIOC. While in grid forming mode, can the inverter be programmed to output negative sequence current, magnitude, and angle?
I believe the answer to that is yes. Lucas, would you mind?
Yes.
Yeah.
We do provide negative sequence even in grid following mode, can be provided grid forming as well. So that's something we have proven over time in models and real projects as well.
Next one. Can you share some typical requirements for black start capabilities in grid forming battery storage?
You want to take?
Yeah, typical requirement would be, for example, you have a gas plant which you need to black start. So not your battery storage plant is the black start for the grid, but it's the black start for the auxiliary power of a gas peaker plant, for example. So all these pumps and auxiliary supply of these gas plants, they need to have, of course, some power source, and they are all connected through a medium voltage grid. And there's lots of transformers, so there's lots of inrush current you need to handle, and depending on the loads and the sequence of how these loads will be connected. So that is a typical application we see. The inverters needs to be sized correctly to provide that current. In the first place, of course, create the voltage, create the grid, and have the sequence of connecting all the loads, providing the loads. Then the generators of the gas peaker plant would take over, and then we will synchronize back to the existing grid. But the portion of our inverter power to that gas power plant is, of course, very minor. It's only for the auxiliary. So we're talking about maybe 20 megawatts or something like that. But depending on the size of the plant and depending on other loads, it can be higher as well.
Sounds good. The next one, which Drupe mode is more common in grid forming applications, U of Q or F of P?
Well, the F of P, of course, is most commonly used, but we use both. Both have to be used because voltage and frequency is always fluctuating. So you have to use both in microgrid modes.
Next one is, does grid forming inverter need PLL to detect frequency and phase during transient, particularly under unbalanced faults?
No. No.
Does virtual impedance go against the desired behavior of voltage source behind small impedance?
The virtual impedance is needed in order to protect the inverter and to provide a steady state short circuit current into the fault. That's our way of doing that. And there may be others doing it differently, but that's the SMA approach, which works over decades annually.
Yeah, I mean, it's current limiting device. You have to find some way to limit current. Is there any difference between the physical inertia and the controlled inertia? Does controlled inertia have a duration limit or other limitations?
I don't know if I understand the question correctly. Can you repeat it again?
I think the question was,
I guess it's asking, well, it says controlled inertia, so I wouldn't call it that from grid forming because it's not controlled activated, right? Inertia is kind of an inherent response from a grid forming inverter, but it's asking what's the difference between physical inertia and grid forming inertia, if you will.
I understood it to be comparing it against like a synchronous machine compared to IVR provided inertia.
Yeah.
I think it's, if you talk about the quantity, if you quantify the inertia, that's a fixed value of the synchronous machine. Whereas with an inverter, you can design to a specified inertial value. And then within that design, you can parameterize that value to whatever you need it to be based on the stability study. So it's much more flexible asset in many aspects, not just inertia, but in short circuit level as well, as Lucas showed us on his example. It's a much more flexible asset, I think, to the grid operator. And as such, it can evolve with the grid over time. So you can do a restudy 5 years from now and find that you need more inertia, and you can, tune your asset accordingly.
Right. I'll try to hit the last one. I think it's an interesting question. When we use the term grid forming, is it determined at the plant level or inverter level? And if it is at plant level, do all inverters need to be grid forming?
It is an interesting one. So you can talk about these capabilities at the inverter level or at the POI. For example, we provide inertia, as you've heard from us here today over the last hour. We tend to talk about inertia at the inverter terminals, and we talk about how the inverter is able to produce an inertial behavior. But at the same time, what you really care about is what's happening at the POI, right? How does that entire plant behave towards the grid, and how does it provide stability to the grid? And that's a measurement at the POI. And you can implement, SMA has implemented at our power plant controller, through the power plant controller, the ability to have an inertial response consistently. You have to control all of the inverters in a structured way within a plant. And each inverter might have batteries behind it that have different states of charge. So you have to be able to manage all of those complexities to provide the right response at the POI. And SMA does that through our plant controller.
Right. Thanks, Frank. We're at the top of the hour, so I would like to respect your hard deadline there. Just would like to thank you both, Frank and Lucas, for really informative presentation, and the audience for attention and great questions. As I mentioned earlier, an email will go out once the video file has been posted, and we will try to get answers to all questions that didn't get answered during the webinar. The next ESIG webinar will be on interregional transmission and resilience on August 8th at 4 p.m. Eastern Time, and more details, including registration, are already available on ESIG event page. Further information on all of our webinars and meetings can be found on our website at www.esig.energy under events, and our newsletters and informational emails, and you are all invited to attend. Frank, Lucas, once again, thanks for your presentation, and everybody, thanks for your interest. We look forward to seeing you again in the near future, and in the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon.
Thanks for having us.
Thanks.
Thank you.
Bye.